In this video, we're going to talk about another synthesis of alkyl halides, and in this case, we're going to talk about allylic bromination. So allylic bromination means we are going to add a bromine to an alkene in the allylic position. So the allylic position is if I have a double bond, one carbon removed is considered your allylic position. So that is the carbon to which we're going to add a bromine. To do this reaction, we are going to use what is called N-bromo succinamide, excuse me, if I can write today. And as you can tell, since that's complicated, there is an abbreviation that's used for this, just NBS. That's what you will see it typically referred to as. You do need light, just like we did with the radical reaction, because this is also a radical reaction. And you're adding bromine to the allylic position, and you keep the double bond. So if you're trying to do a reaction where you have a bromine, one carbon removed from a double bond in your product, this is going to be your best synthesis route. NBS, the structure is known. It's not overly complicated, but again, it's not something that you're going to want to draw over an arrow all of the time, which is why we just say NBS whenever we are writing it as a reagent. This forms a bromine radical when exposed to light. And then the rest of the reaction is not overly surprising. We're going to remove an allylic hydrogen from the starting material, produce a radical, and then the bromine is going to add. So let's take a look at what that mechanism would look like in a specific example. So here's the alkene that I'm going to start with. I'm going to react it with NBS and light. And I'm going to add the bromine to the allylic position. Okay. We will find that we actually also get a second product from this. We will also produce this product. So by showing you the mechanism here, we will figure out why we get both products. So that NBS and light is where we're going to get our bromine radical from. Then that is going to react with our starting material. We have, in this case, two allylic hydrogens. So the bromine radical is going to pull off one of those hydrogens and produce an allylic radical. So I have HBr as a byproduct again. And then here is the allylic radical that is formed. Now having a radical right next to a double bond opens us up for some resonance structures. So what can happen is that radical electron and one from the double bond can move in to form a new double bond, and the second from the original double bond becomes a radical. So the double bond is now in the middle, and the radical is now out here on the end. So with two different radicals, now I have two locations that a bromine radical could come and add to. Let's switch colors so we're not mixing up our arrows here. So the bromine radical and the allylic radical can come together, and my bromine can add to that what we saw as our original allylic position. With the other radical that's formed by resonance, I can add the bromine on the end. So there is the reasoning for getting two products. Now the question is, which one is more likely to form? Which is the major product and which is the minor product? The less substituted radical is easier for the bromine to come in and attack. So here we have a primary radical. Even though it's less stable than the secondary radical, the original one, it is stabilized by the resonance. It does form. And with that primary radical being out there in the open, the bromine radical can more easily come in and attach. So that is going to be the major product. And then the more kind of hindered radical will be the minor. It's more difficult for that bromine to get in there. The other way to think about this, and this is most of the time parallel here, is your more substituted double bond, meaning more carbons on the double bond, is also the major product. So here my major product, my double bond has 2 carbon groups coming off of it. In the less substituted version, there's only 1, all right? So the less hindered radical is going to be your major product. That's the best way to think about it. So because there's resonance, we get mixture products. The reaction is more selective though than just alkyl halogenation, because we are limited to originally moving the allylic hydrogens, right? We never even considered touching these hydrogens on the CH3 on the end. It's only going to go for the allylic position. So there is a little bit more control. Once you have an allylic bromide, you can do further reactions to produce dienes. So looking at an example here, I'm going to take my allylic bromide from the previous problem. I can do an elimination reaction by adding a base. So potassium hydroxide is a great base for this. And what happens is I pull off the bromine and one of the adjacent hydrogens to make HBr. And then that leaves room to now produce a second double bond. Because there's 2 double bonds here connected or next to each other, we call this a diene. One more example to look at just in general here for the NBS reaction. I'm going to start with this alkane, react it with NBS and light, and I want you to explain why this is the major product that is produced. So notice the double bond has moved. So I'm not simply just removing the allylic hydrogens and replacing it with a bromine. Remember that previous example, we showed how we have resonant structures that can lead to other products. So let's see if that gets us to our right answer. So we've got a couple allylic hydrogens. There's actually a total of 4. Notice there is symmetry in this molecule. So the 2 on the left and the 2 on the right are identical to each other. So really there's only one option. So I'm going to remove one of those allylic hydrogens to produce the radical. Now I have the radical adjacent to the double bond, so I do have resonance. Let's show what that resonance structure would look like. So by moving the radical with resonance, I now have the double bond where I want it in the product, and my radical now is less hindered, and it's out here on a primary carbon, which is where the bromine adds. So that's the explanation for why this is the major product. We can get there through resonance of the radical. The radical produced is less hindered than the original radical produced, so that's where the bromine prefers to add, and therefore why the structure shown is the major product.